Hello and welcome everyone. My name is Hannah Mason. I'm a technical editor at Composites World. I want to thank you for joining us today for this webinar titled Enabling Next Generation Composites with Circular Carbon Materials, brought to you by Composites World and presented by Mito Material Solutions. Our presenter today is Kevin Keith, CTO and co-founder of Mito Material Solutions. Kevin holds a degree in mechanical engineering, and he was named a featured honoree in the 2020 Forbes 30 Under 30 Manufacturing and Industry list, along with Mito's co-founder and CEO, Haley Keith. He's going to be talking today about a new, more sustainable form of graphene made from reclaimed methane. However, functionalization is needed to unlock graphene's full range of properties and to make these materials useful in composites. So in this webinar, he will be discussing how to bring functionalization and multifunctionality to this new green graphene. There will be a Q&A session at the end of Kevin's presentation today. And so attendees, you can submit a question at any time during the webinar in the Q&A field that you see on your screen, and we'll get to as many of these as we can at the end of the presentation. I do also want to note that the webinar is being recorded, and when complete, will be made available to you via email from Composites World, so you'll be able to watch it back later. Without further ado, welcome, Kevin. It's all yours.
Awesome. Thank you so much. Hey, everyone. Kevin Keith, CTO at Mito Materials. And at Mito, we functionalize graphene and carbon materials. So today, I want to talk about the next generation of composites with circular carbon materials. What I mean by that is these circular carbons are made from reclaimed processes that have gone through different processing methods. So before we get too far into that, refresh a course on graphene and what it is and what drives it. So I'm very sure that most everybody here is very aware of what graphene is, but setting the tone, graphene is a class of materials ranging from 1 to 10 layers of carbon allotropes. So these 4 pictures here are different forms of graphene, whether it's more micron size, nano size, different layer counts, they're all classified as graphene. Within that structure, you have different morphologies, which dictates integration and performance values, as well as the sources. The source of the graphene drives price, quality, and morphology. And we'll get a little bit more into that later, as well as the compatibility of the graphenes. So the defect count, the residuals, they can make for poor performance if you don't tailor it just right. So at Mito Materials, what we do is we source any of these graphenes from the market, from any feedstock. We functionalize on top of them to make them more polymerically compatible. So when we have a product idea or a customer comes to us with a certain need, they say they need increased mechanical performance or thermal interaction. We look at our feedstocks available that we have quantified and qualified for our own internal processes according to our own standards and ISO standards. And we pair that with certain chemistries to better compatibilize those to then interact, disperse into those systems. We have patented chemistries as well as a vast array of company trade secrets. And we know that functionalization is key to performance. Not only do we know that, but the market realizes that as well. And that is why we are the first and only verified functionalized graphene on the market, verified by an independent third party, the Graphene Council. So to give you an idea of the impact of graphene materials, we have a functionalized product called Mito Ego that at 0.1% by weight loading, it can make products up to 100% stronger or up to 35% lighter. And what that really means is that with 2 pounds of this material, you're able to lightweight enough plastic in 5 Ford F-150s by 35%, or increase the strength of 3,000 carbon fiber bike frames by 100% with the same drop-in solution. That's because we tailored the functionality of this system to be able to be polymerically compatible, easily dispersed into a wide range of materials. Now, what that really means with other graphene feedstocks is here you'll see 3 different colors, and they're all different graphene feedstocks ranging from nano graphite all the way down to few layer graphene. So on the left in the yellow is that same feedstock functionalized with our chemistries. And you'll see that with these different chemistries, you're able to disperse into isopropyl alcohol a lot more efficiently with very low energy input, therefore allowing for a greater interaction within different polymer systems without needing special mixing equipment. Now, graphene being family of materials can be made in a range of different ways. There's what's called tops down, which is exfoliated graphite from mechanical or chemical processes. You could do graphene oxide, a whole bunch of different stuff. But specifically, I want to focus on the bottoms up approach. So, bottoms up graphene is made from three different processes: chemical synthesis, gas phase growth, and epitaxial growth. Epitaxial growth, big word, but in essence, you either have a couple of different variations of CVD or hydrocarbon processing. So, with chemical synthesis specifically, you have hydrocarbon cracking. You can put that through a number of different processes, uh, have a bunch of different levers you can pull to have different morphologies, different structures made up. With those levers, you can make monolayer graphene all the way up to nanographite, carbon black, that type of carbon materials. The main applications for this processing method: composites, lubricants, concretes, batteries, even really anything that is not chemical vapor deposition or CVD. Then you have epitaxial growth, where it's a crystalline growth CVD. Picture, if anybody has kids, making rock candy is a very simple way to where you have a very highly concentrated sugar water. And as that water dries out, crystals grow, and then that rock candy forms around that single crystal. Same thing with epitaxial growth, in that you have a certain solution that, as a crystal forms on a substrate, the rest of the carbon crystals grow around it. You can have mono few layer deposition from this. Main applications from this are capacitors and chips, very highly dependent on thermal and electrical throughput, that you can have smaller scale production methods because of that crystalline growth. Then you have gas phase growth, which is a catalyst driven CVD. So think you have a gas that is carbon rich within a certain machine that has silicone wafer. You introduce a catalyst, it cracks that carbon apart, the carbon snaps to that silicone wafer, and out comes waste. You can have mono and few layer deposition for this. Main application: sensors, electronics. Some really amazing sensors can be made with this gas phase growth method, because you're able to sense electron movement and have very, very, very sensitive sensors that has actually unlocked a lot of great potential. Now, with those various forms of graphene, you have your number of layers versus number of defects. And so each color on this graph denotes a different production method, whether it's that tops down from that graphite or bottoms up from these chemical processes. Now, you'll see here that the higher number of layers, the fewer defects you can have, but that's mainly for liquid phase exfoliation. The fewer number of layers, though, the higher the price per kilo that you're going to have to be paying for it. So every production method has its limits, but you'll see here within the red dotted line, this green bubble right here is chemical synthesis. So you can have a very few number of layers, very few number of defects, because you can fine tune what is and isn't on that graphene or carbon particle. So with that chemical synthesis, you can produce it from a wide range of carbon containing structures. So hydrocarbons, think acetylene, methane, ethanol, butane, any of those components can be cracked apart with different pyrolysis methods. Biofeedstocks, polymers, even feeding it into certain processing methods, as well as coke, waste coal, you name it, you can crack it apart and have this chemical synthesis graphene come out of the on the other side. Now, the various cracking methods that can be used to blow these apart to have these carbon allotropes reform into themselves. Uh, there's pyrolysis, essentially controlled explosions using, I don't know, anything like a spark plug within an inert environment with a little bit of oxygen to control that explosion. Uh, Plasma reactions, so using microwaves to have a really high heat, high throughput system that you can start pulling levers on what inert gases you're using within that plasma process, your feed rate, your heat, to have a monolayer come out the other side, carbon black. It's a very wide range of what you can do with that. So, with those feed rates and feedstocks, you can produce a wide range of different morphologies, as well as chemical structures on there. Being that you're feeding hydrocarbons into the system, depending on what hydrocarbon you feed into there, if you feed it fast enough and at a cool enough temperature, you can have PAH particles on there, uh, which are, pros and cons to that, depending on what application you're going for. So you can create highly wrinkled structures, highly flat structures, very small, large. It's a really easy way to get the metals out of graphite particles. So with tops down processes, you have to mine graphite from the earth. And because it's, of course, coming from the earth, you have different mineral compounds that are kind of contaminants in that system. With this chemical synthesis method, you're able to have a very finely tuned carbon particle to where it's a very, very pure with very low defects. So, because of that, you have a very diverse compatibility. So, the feedstocks and method enables different ionic compatibilities that you can actually have real time monitoring. So, as it's going through this pyrolysis or plasma method, you can have in situ monitoring to where you can take real time readings of layer count, crystallinity, uh, carbon content to where you know in real time if you're hitting your QA/QC. So that way you don't have to make a batch, go back to the bench top, run it through, and spend more time doing it that way. So you can in real time dial in what is going on. With that dialing in, you can fine tune the structures. So, like any production method, you can look at feedstocks and heat. Feed rate enables different morphologies, which have different benefits for composites and lubricants and concrete, layer count, all that fun stuff. And because you're feeding in these hydrocarbons or bio waste, polymers, that type of stuff, you're in a way going through a carbon sequestration. Typically, with hydrogen production, for instance, people put methane through a pyrolysis method. Out the other end comes a hydrogen rich methane and carbon particles. Depending on their whole setup, again, going back to the tunable structures, you either have carbon black, graphene, or even solid carbon dioxide. Most of the time, currently, that solid carbon is buried in the ground. ARPA-E, through the Department of Energy, did a whole study that in order to make hydrogen a viable fuel source to get the cost down, that solid carbon has to be commercialized. And it's not even a crazy amount. It's something like $200 a ton that it has to be commercialized at in order to cut the cost of that hydrogen in half. So, really, on the other side of this pyrolysis method, cracking that methane, you're able to create this value add product that is then able to be put into composites and rubbers and cement to have a higher performing system to lightweight materials. So, it's a really interesting circular method that you can start implementing these types of materials. So, some public use cases of these, a bottoms up fuel layer graphene that's made from pyrolysis was integrated at 0.04% by mass of the cement within that concrete. And with this material, they were able to show an increase in compressive strength by 70% in the early cure stages. That's a pretty big jump for such a critical time within the life of concrete being set up. And after that 28-day cure cycle, it increased that compressive strength by 15%. So, with these metrics in mind, and with a combination of a reduced porosity and critical pore size of 50%, it has the potential to reduce global warming potential of concrete by 15% just with that little bit of material sprinkled in. Now, another use case of these bottoms up graphenes is that this nanographite from a methane pyrolysis was integrated into a truck tire, of all things. Uh, Tires, as of right now, they use carbon black because of its rolling resistance properties and its longevity. And so whenever they put this nanographite into this truck tire, what they found is that it decreased rolling resistance by 23%. And that should correlate to an estimated 3% annual fuel saving. Now, to put that in perspective, worldwide, if we were to use these tires, that's 29 gigatons of CO2 reduced annually before you even factor in the fact you're cracking the methane and creating this value added carbon material. So, by the time that you're able to take methane, which is something like 10x more pollutive than CO2 in a very short amount of time, turn it into this value add product and then getting it into tires that are then reducing your CO2 output is a huge step towards in the right direction. Now, with these bottoms up graphenes, Mito has functionalized on top of them. And what we do within these composite materials is that we look at certain systems, whether it's a polyester, polypropylene, epoxy system, and we're able to fine tune, functionalize on top of, and deploy these materials to create some really wild characteristics. So, depending on physical and chemical nature of the feedstock, our customers out in the field are experiencing 3 times electrical conductivity increases. So, we're able to supplant a lot of different other additives that were primarily being used to slightly increase conductivity, but it added a whole bunch of weight. So we're talking, you know, 0.02 to 0.2% loading by weight into the resin, and you're getting these conductivity increases. With these other materials, we're able to reduce materials by 30% with 0.1% by weight of our materials. So they're able to just disperse it in on site, make parts. And what they're finding is that with 30% less material and 0.1% of our product, they're able to create a much stronger system that still passes QA/QC. So with these chemistries, we're creating these shelf-stable systems that are able to go into water and organic solutions like acetone, isopropyl alcohol, NMP, that type of stuff that is very easy to mix in, that requires no special mixing equipment. I currently have samples in the back that have been suspended in water at 7% for about a year right now. Just with these bottoms up chemistries that we haven't been able to see in the marketplace. So we're actively deploying these into the field. And I do believe that using these quote green graphenes in order to have a more circular economy within the composites industry is very much needed for a long list of reasons, but mainly because we all know composite materials have a huge carbon footprint. And if we're able to reduce that by using a more synthetic, reclaimed carbon material in order to boost properties and reduce our materials, I think that's a huge win for the industry as a whole. So, with that, Q&A. Thank you all for taking the time to join the webinar, and I look forward to your questions. Thank you.
All right. Thank you so much, Kevin. That was great. So like Kevin said, we've now reached the kind of Q&A portion of the webinar. So if you have a question, now's the time. Feel free to submit it in the Q&A tab. And we'll start with some questions that have already been submitted. So the first question, he says, they say that they produce fiberglass floor joists and are looking for ways to decrease deflection by adjusting their formulas. Could these products be incorporated into their epoxy matrix?
Yeah, absolutely. Our formulas specialize in increasing the stiffness in G1C. So, yes.
Okay. Next question. You talked about improvements in electrical conductivity. Do you see the same trends in thermal conductivity?
It totally depends on morphology and physical structure. If I have a larger but flatter particle, yes, but not 3x. Typically, with that 3x electrical conductivity, we have somewhat of a thermal conductivity increase, something along the lines of 20 to 30%, but definitely not 3x.
Okay. Related question, somebody said, how can that 3 times conductivity be used? Or what would
Ooh, so
Okay,
Sky's
sweet.
the limit on that one. If you so ooh, lots of ways. So you can do static dissipative properties within composite materials. You can do EMI shielding if you pair that with kind of like a skinning system to be able to um, have more of a Faraday's cage on the outside of like airplane wing, whatever it is. Uh, Heating elements as well. If you have a much better dielectric breakdown, as well as kind of a resistive heating element, you're able to have a thinly veiled, a thin coating of this highly conductive system that doesn't add any weight. So you have more de-icing capabilities, defogging, to where you're able to have, whether it's a airplane wing or a windshield, to where you don't have to have fan blowers, de-icing liquids, that type of stuff. So uh, really the imagination is the limit on how you can or how you want to use those electrical increases.
The next question is, if you were to add 0.1% into ABS, what weight reduction would you expect? Or what type of range, I guess?
What a loaded question. Thanks for asking that. So it depends on the chemistry of the additive that you put in there. Email me. We can take that kind of out of here because that's a much deeper dive than I can answer in a webinar, unfortunately.
Okay. Next question. Do you have a list of solvents or systems that you have demonstrated improved dispersion in?
Yes. Water, IPA, acetone, THF, NMP. If you really want to get crazy, MEKP, polyester, vinyl ester, epoxy, both BPA and BPF. I mean, really any system that you need to disperse into, we've done it and we've kept it stable for the most part. Whenever we increase dispersibility, what we look at is how well does it wet out and how well does it maintain that particle size and not agglomerate. Because really what you're looking at is a zeta potential on how that particle interacts within that system. So really any polar organic solvent that we're looking at disperses very well into. Epoxies, polyesters, and vinyl esters, really great at, to the point that I can go in on site with just a drum mixer, put my powder in there, and it disperses amazingly, and people are able to actually take up to 30% of their material out just by doing that process.
Okay. What is the upper limit for how much you can include in an application, and what happens if you have too much?
Graphene is one of those weird materials that less is more. For instance, if you include too much, you start getting a decrease in mechanical properties. And when I say too much, I'm talking 1 to 2%. At that point, you start getting bigger decreases, specifically in epoxy carbon fiber systems. Most systems degrade 5 to 25% at that 1% loading. I typically don't like going above that because at that point it becomes not only cost prohibitive, but you start increasing the viscosity a lot, to the point where, for instance, we've done viscosity studies studying how it behaves whenever it's loaded. And so when we've loaded our materials, I believe it was at 5% by weight into a BPF epoxy, viscosity of about 8,300 centipoise. It jumped it up to the viscosity of 828, which is about 13,000 centipoise. So there's a large jump there. Now, that's with just ego. Whenever you're looking at other bottoms-up functionalized materials, you can load it about 1 to 2% and have a slight increase in viscosity. But you're also looking at different aspects of electrical properties, thermal properties. Do I see any other mechanical behaviors in here that, while I'm not looking at, flex, is there a kind of a different feel about the system? Because when I look at sports, when I talk to sports people, they care about mechanical performance, but they care about how it feels. And that's such a human objective aspect that it just totally depends on who's touching it and when. So on the other end, 0.05, 0.02, 0.01, you can start doing some crazy properties with that as well. There have been plenty of studies out there that within lubricants, loading a bottoms up graphene at very, very, very low concentrations, you start increasing wear life by 24x, reducing coefficient of friction by 30%, and you start getting these crazy properties with a, a literal dusting of powder into a 55-gallon barrel.
Okay. Next question goes back to the concrete application you mentioned. Mm-hmm. Have any accelerated aging studies been done on concrete to see if the 15% post-cure strength may be retained long-term?
Yeah, I believe that is ongoing right now. That one, they just did a quick study. There have been other people out there, other graphene companies that have done the quote living labs. It's like one of my favorite words because I like doing these live trials. Anyway, so people have put graphene into concrete and done these living labs and just let it sit out in the sun for 6 months. There have been some good results. There have been some bad results. I've seen a sample one time that I was there when they freshly poured a slab and they didn't put any rebar in it, no reinforcement, and they used 30% less material. And in the lab, it showed that it had really great compressive strength. It had some really interesting post-cure properties. But about 6 months later, I was back at that same slab. And when I looked at that slab as compared to the much older concrete around it, that same little pour looked way older. It was pitted. It had some algae on it. It was a little deformed. So it definitely depends on what type of graphene, the functionalities, really the whole aspect of that graphene, how it makes that concrete perform. I do believe that certain graphenes with certain chemical functionalities can impart some really great long-term characteristics on concrete. And I believe that's going on right now. I mean, in Australia, UK, I think over in Malaysia as well. There's plenty of studies going on. And I think there should be graphene enhanced concrete in the next 3 to 5 years. More worldwide. There are smaller firms here in the US that are actively deploying that. That I think the longest term pour that they have is 7 years and it has no stress cracks. So again, it totally depends on what graphene system you plug into that concrete.
Okay. Next question. How does this bottom-up generated graphene affect the toughness when incorporated in composites? I guess, is there a difference between that and the top-down?
Yes and no, there is a difference. If you were to plug in just a bottoms-up graphene into a composite, you're going to have a lot of difficulty getting that to be well dispersed. We do see that with our functionalities, much easier to disperse. And whenever we compare apples to apples with a functionalized version as to a non-functionalized version, leaps and bounds. We've seen that with non-functionalized bottoms up, 0.1%, you actually have a decrease in properties, about 5 to 10%. Again, carbon fiber, bio-based epoxy, we were looking at how it would behave within more or less a ski build. Whenever we plug in the functionalized bottoms-up graphene of that same nature, it performed much better. We had a strength increase of 25%. Typically, we see a G1C increase of like 25, 30% with just that 0.1% by weight loading. So I mean, like with anything composites, it can vary wildly depending on your epoxy and hardener type. But typically, we see with that functionality, we're holding everything together better. And that's what we believe is very much driving that G1C toughness increase.
Okay. The next question is, could used pre-preg carbon materials in the general sporting goods industry be recycled efficiently as a source of feedstock, specifically referring to the mountains of used carbon composite skis, bicycle frames, wheel rims, etc.?
Yeah, that is a question that a lot of different people are trying to scale up right now. They can do it on a lab scale. What comes out the other side is not 99 or even 98% pure carbon content. It's sitting in the realm of about 95, 94%, which means on the other side of that, you have other complex chemistries like amines are in there, you have PAHs, you have hydrogens, oxygens. It can be a kind of a nasty output uh, on top of trying to delineate the carbon from the epoxy. So I think it will eventually get there, but I think it's going to take a lot of fine tuning in order to get it to an industrial scale. Being able to crack apart such an aggressively cross-linked system like epoxy and carbon fiber, it takes a ton of energy. But I think eventually we'll get there. Today, smaller quantities, but we'll see what's going to be coming down the pipeline in the next 3-ish years.
Okay, interesting. What is the difference between electrical conductivity between graphene and carbon fiber? And what are the advantages, I guess, of graphene for electrical conductivity?
If I wanted to be an absolute nerd and compare apples to apples, carbon fiber electrical conductivity, if I remember right, if you just measure the fiber by itself, it's about 300 Siemens per centimeter. With graphene, I think it's in the order of like 5,000 Siemens per centimeter or something like that. If I just took a graphene flake and I measured that, it's a crazy amount. Now, neither carbon fiber or graphene is really used by itself. And whenever you're measuring the electrical conductivity of graphene, you have 100% carbon. But whenever I'm looking at, say, a 1 kilogram of composite and 33% of that is resin, then I put in 0.1% of that carbon material into there, I really have 0.3 grams of a pure carbon material in 1,000 grams. It's really a drop of water in a bucket. So whenever it interacts, though, it is able to increase it to that 3x component. But being able to compare apples to apples for carbon fiber versus graphene, that is a really hard metric to quantify. So I typically look at the system as a whole. So whenever I look at a carbon fiber system as compared to a graphene enhanced carbon fiber system, that's where we're getting that 3x increases at.
Okay. From a chemistry perspective, how do your graphene materials differ from the structure of coal and the properties that they provide?
That comes down to, okay, so metallurgical lesson a little bit. Metals have certain grain structures. So you have like a BCC type thing to where you have either a crystalline or more of an amorphous type structure. Same thing goes with polymers and the fact that you have amorphous and crystalline structures. You either have essentially a pile of spaghetti noodles or you have a very ordered system. Same thing can happen with graphene. Graphene can come in this very crystalline, very jagged form, or it can come in more of an amorphous, crumpled, very pliable form as well. Coal, from my understanding, is very, very, very amorphous. It is on the lines of carbon black, and the fact that you can shave it up as much as you want, but it is thousands and thousands of layers of carbon, whenever you have these thousands of layers of carbon trying to be dispersed, let's just hypothetically say into a composite, you have these platelets that are randomly oriented in different directions. And because there's such large layers, your electrical and thermal properties can't get through all of those layers because it's anisotropic. So in reality, you're dispersing pencil lead, coal, into your system. With graphene, you have a much smaller particle that at that point you're having electron quantum type properties take over, because you can have sp2, sp3 carbon type systems uh, be the main driver of electrical and thermal properties. Whenever you have coal, a more amorphous structure, it's really hard to delineate these sp2, sp3 sites to be able to really tease out those systems. So coal can be used as a feedstock for this bottoms up process, to where you can blow it apart, you can fine tune it, you can get graphene out of that. But being able to just take coal and put it into the system, uh, I haven't seen that work.
Okay. Next question, I think goes back to kind of the video examples you were showing, kind of dispersing into clear liquid in the video. They say it appears that the samples you showed being dispersed, your ego turns clear materials black. At the low levels that you're using, would your graphene impact the color of a white coating for a part?
Ooh, depends. Well, at that loading, about 0.1%. So if I put it into a composite material, it turns it like a smoky gray. That's even with fiberglass involved. That's about a 50-50 resin to fiber by weight ratio. Whenever it comes to a white component, if you can get the loading and still get the benefits out at, say, 0.05, 0.02%, it would make it a little bit more dingy, but it wouldn't be making it gray. It would be really interesting to see how that would perform and what that would look like. Whenever I've put it into coatings that have typically come out white, and I've taken our water dispersions that I've functionalized specifically for coatings, put it into that system, it does turn it kind of a grayish. Really interested to hear what application you have in mind with that. So email me, and I want to talk further.
Okay. Next question might be a bit specific. We'll see what your thoughts are on this. Do you think that epoxy resin carbon fiber reinforced composites could benefit in terms of fire retardancy and gas barrier properties for use in a type 4 or 5 hydrogen storage tank? Using your material, I suppose.
Yeah. Yes. So twofold. I currently have a grant with the state of Indiana studying exactly those properties with gas barrier, showing functionalized bottoms up and tops down, because I want to cover my bases, how epoxy carbon fiber systems can improve gas barrier properties. Papers have really shown that it can do that. I'm aiming for a lower loading with functionalized material, because if I look at those papers, they loaded in there at like 1-2% with a much larger plate, a much larger graphene platelet size, because essentially you're really trying to impede how that system gets through. Now, on the flame retardancy side, as much as I can divulge, because it's public knowledge, I do have work going on with an adhesive company for EV batteries for specific flame retardant properties. All I can say is that those are going very well, and we have shown that our functionalized materials do increase flame retardant properties. Should, I do believe, correlate over to composite materials as well.
Okay. Could you use these materials to improve radar invisibility instead of a metal like copper?
Oh, I've been kicking around that idea for a couple of years now. Yes, I do think so. I think there's some possibilities for very unique delivery methods to where you can maybe even retrofit planes to do that. Uh, Besides, making new composite structures, I think there's different ways to do that. But yes, definitely. I have some ideas for that, but I just haven't had anybody interested enough to bite onto it.
Well, maybe you have one. We'll see.
I hope.
Okay. Next question. They say they're wondering about the electrical conductivity and short potential when processing. Are there any handling considerations to consider when processing?
That's a really great question. Static dissipative properties come with an increase in electrical conductivity. So whenever you have electrical insulation, you're essentially creating a grounding scenario. So I have not had anybody have any equipment get shorted out by our materials. And we've put it through chopper gun, resin infusion, hand layup, pultrusion, extrusion, twin screw compounding. Everybody's raised those questions, but nobody's experienced it. Handling considerations, considering we can sell our products in a very wide range of delivery methods, whether it's in liquid dispersion, pellet, master batch, or even powder form for our customers to take that on themselves. The powder aspect, standard powder handling procedures apply. If you're familiar with handling talc, sodium bicarbonate, like that type of stuff that goes into composites as like mineral fillers, you know how to handle this material. All of our functionalities, they make the particles micron size by default. That's by design. So standard PPE equipment when handling it, gloves, smock, mask, that type of stuff. It's pretty easy to handle. That hasn't scared anybody away.
Okay. Are there certain morphologies of graphene that are more or less compatible with Mito's process?
No. Certain morphologies are more suited for certain applications, but our processes are not driven by morphologies.
Okay. Does your dispersion of graphene in a variety of solvents and systems that you mentioned have any other additives to achieve long-term stability?
No.
Okay. Do you see any benefits to adding graphene to metal, such as magnesium alloy in thixomolding for strength increases and weight reduction?
I think so. I've been reading a lot about this topic, and there are papers that show that you can incorporate graphene at least into lower melting point metals, because graphene has a ultimate degradation point of something like, again, absolutely depending on feedstock morphology, layer count, like all that stuff, anywhere between like 6 and 900 C. The melting point, so for instance, one paper, copper, melting point of copper is well beyond that 6 to 900 Celsius. And so in order to get it into the copper, you have to do some wonky things. But once you do those wonky things, you can actually increase thermal conductivity 100% by incorporating 0.5% of graphene into the system. If it's scalable, I don't know. But if you're doing smelting and doing mold casting with that sort of stuff, I don't think it's going to work, because ultimately you're throwing coke into the system. It's a really expensive coke. So there's info that you can, but it's very specific manufacturing methods.
Okay, interesting. Is there any significant anisotropy introduced from this additive, particularly in electrical properties?
So tough to say, because on one hand, anisotropy is measured within a film. And to measure it within a film, you have to cast that pure system, of course, into a sheet. Graphene, in order to get it to cast into a sheet like that, is extremely difficult. If I were to put it into a polymer, of course, I'm mixing it up and then I'm casting it, and then I don't have a way to control the sheet orientation. If I were to do just a graphene without functionality, I would hedge bets that anisotropy is definitely is there, to where we have conductivity in one direction, insulation in the through plane. I've typically seen that with our functionalized materials, we don't have that anisotropy. That whenever we have 0.1% into a carbon fiber composite, our own internal studies have shown that in the planar direction, we have a 68% increase in electrical conductivity, and in the through plane of all things, 86% increase in electrical conductivity. So it's close. It's not anything detrimental of 150 and 0%. So there are ways to get around it, and I think our functionalities are able to bring that to the table.
Okay. The next question asks, do you sell the graphene as a powder or as a dispersion? I guess, can you maybe speak to what forms of your products that you sell?
Yeah, both. We can do master batches of that powdered product. So you can buy the product outright. We have sample packs that are available. Then we can do master batches into organic solvents, epoxies, really any system that you want or need it in. And then we can do thermoplastic master batches as well. We have a wide network of partners that we're able to get that into pellets, rotomolding powders, that type of stuff. So if you want it, I can pull on people and I can get it.
Okay. Next question. I imagine it depends, but kind of to what degree is strength affected in a fiber reinforced polymer when graphene is added?
Yeah, I've seen it, in some epoxy systems it flatlines. In others, putting that functionalized material into the system, I've seen it, depending on what metric you're measuring, flex strength increase 70-80%. I've also seen torque strength increases within rods increase as high as 50%. So definitely depends on what properties you're looking at, UD, pre-preg, hand layup, that type of stuff. You can get some really good strength increases. Now, whether you want to utilize that to use less material, totally up to you. But if you're just looking for just an absolute powerhouse of a composite, then incorporating that functionalized material into it is usually the key.
Okay. Do you offer a graphene product that is functionalized to be able to be dispersed within silane or siloxane chemistries? I can't remember if those were on your list earlier.
We can. I haven't had anybody ask that question, but email me, we can talk. I'm sure yes, because ego, for instance, it's paired with POS, which, bear with me, polyhedral oligomeric sulfesquioxane. So it's a silane structure. I'm sure it can go in there. I haven't tried it, so reach out to me.
All right. Next question. How does incorporation of graphene or graphene oxide into high-density polyethylene, HDPE, in linear low-density polyethylene, LLDPE, influence their thermal conductivity? And what mechanisms are responsible for the observed enhancements?
I can't answer that last one because that's trade secret, and I'm pretty sure my boss would have my head on a platter if I do that. In regards to thermal conductivity within, I'll just generalize it in PEs. Graphene oxide, you'd have to make it a powder, and then it would not be good. It would actually become more insulating. If not, you would only get like maybe a couple percentage points increases. That's because of a lot of different aspects of graphene oxide that we've been able to correlate to. Graphene, on the other hand, we've typically seen that if you take a nanographite, because PE is a very cheap material, and so you kind of have to set an upper limit of what you're going to look at in the first place. Nanographite, you can get thermal conductivity increases, therefore processing increases. We've seen typically about 20-ish%. Processing wise, it actually increases that cleanup, that processability significantly. Hasn't really been characterized with hard data, but that's been customer feedback saying, hey, this has been really easy to clean up. I didn't expect this, but it was really nice. So it's there. It's definitely there.
Okay. Related question. Which would be better for thermal conductivity enhancements in HDPE, graphene or carbon nanotubes?
I'm biased. Graphene. So nanotubes are interesting. They have good aspects. If you're putting carbon nanotubes through a compounding process, if you're doing single wall, yeah, I'm sure you'll get it, but those are also very expensive, and they're tubes. So you have, increased surface area, but you also have drastically reduced functionality points. Graphene, on the other hand, you can have more spread out, and of course, you're looking for more spread out kind of touch points to be able to reduce that band gap, to be able to have these thermal conductivity improvements. I like graphene because I can do a lot more with it. Nanotubes are extremely difficult to work with, disperse, functionalize on top of. I mean, it's a laundry list of things. So I tend to stick with graphene and nanographite.
Okay. Do you think dispersion of graphene in the form of a powder is harder than dispersing it in the form of suspension? And do you think that mixing in suspension form can lead to deterioration of mechanical properties of a composite due to evaporation of the solvent?
Excellent question. Dispersion wise, so whether you're comparing dispersing it into a master batch as compared to just dispersing it straight on into your system, a couple scenarios occur. If you're just dispersing into the system and it's a large portion, so like if I'm making, I don't know, hypothetically, 100 kilos of resin, that's easy. You just disperse it straight up, 0.05, 0.1%, 50, 100 grams of product, disperse it in, done. If you are making a composite with 50 grams of epoxy, you're going to want to have a master batch first. So dispersing it into that master batch at 1, 2%, that's easy enough. And then you just let that down to that end value of 0.1%. Whenever it comes to really how you want to go about that, how really you want to slice that cake, it totally depends on your scenario.
Okay. We're getting to the end here. We have one more question. Where all geographically are Mito materials available? This person asks specifically about Asia, so just mainland China and Taiwan?
Okay. That's a great question. We ship worldwide. We can sell worldwide. We have distributors here in the US. We have a distribution network over in Taiwan as well. So products available. So reach out.
Okay. I said that was the last question, but we did have one more come in. So I'll squeeze that one in real quick. Hang in there one more second.
No worries.
With such low percentages of graphene used in these applications, how do you ensure the mixing is uniform?
Yeah, so that's one of the key benefits of our functionalization is that it enables a good dispersion, but you also don't need a totally homogeneous dispersion. So whenever it comes to pure graphene materials, non-functionalized, when I say functionalized, like more than oxygen or amines on there, classical ISO definition that's coming down the pipeline is that oxygen, amines, any element that's just tied on there, not functionalized. Our chemistries allow for a lower barrier of entry to where you don't have to ultrasonicate, you don't have to mix for 30 minutes type of thing. So then you're able to plug it in, disperses, and if you see huge chunks, like I'm talking a centimeter, that's more of a problem. But if you're seeing, little tiny half millimeter flakes, that's generally okay from what we've seen. We have our COV, even with those size of flakes, our COV sits around 3 to 5%. So it's pretty good. I would also like to circle back around. I realize I did not answer the last part of that previous question about how do you ensure you don't have mechanical decreases when you're mixing. You can't really. You typically with us, we like to use whenever we're mixing en masse toll blenders because they have the experience of limited handling within those epoxy systems that ensures that it has a good dispersion, but you're also not causing cleaving of those polymer arms. So it really totally depends on the polymer system you're plugging into to make sure that you're not causing that cleaving. That's typically why we we typically lean towards a master batch unless they're doing a 55-gallon barrel all at once and they have the capabilities that they're already going to be doing a high shear mix or mixing in other mineral fillers that we're just going to piggyback and sneak in there anyway because they're already going to be mixing in the first place.
All right, excellent. So we've now come to the end of the webinar. It's a great presentation, great Q&A session. Love hearing all the questions and engagement about this topic. Thank you so much, Kevin, for being here and for this presentation. We really appreciate it.
Yeah, absolutely. Thank you, everybody.
Yeah, thanks for attendees. We appreciate you being here. Hope you'll join us again for the next Composites World webinar. For more info, of course, visit compositesworld.com. Have a good day, everyone.